Hello, welcome to this material characterization online course organized by NPTEL. In the last couple of classes, we are taking scanning electron microscopy case studies in the form of tutorial classes. I would like to continue in this class also the same case studies. What we have seen so far in the last couple of classes, we have taken some of the examples like alumina, how to polish them and how to proceed with the fracture analysis. In all these cases, I just emphasized a fact that when you go for these kind of characterization techniques, which involves lot more time and precision, it is better to have a clear cut objectives well defined before you enter the lab, and some of the objectives I have just shown in the case studies. For example, if you look at this alumina, we were interested in looking at the grain size and grain boundaries, and then whether the grain boundaries are free from the second phase particles and so on. And then I also just demonstrated this micrograph, which is a fracture surface, and then which revealing the intergranular fractures. And of course, I also mentioned the difference between these two is because nothing to do with the sample, but the detector system, which has got an in-lens detector in this case. That is why you can see the better contrast in this surface. Then I showed you the fracture surface of this, the thermally etched alumina, where intergranular and intragranular and then kind of a pore inside the material, and this is how we discussed as a case study 1. And then we also looked at this micrograph, where I showed the SEM micrograph of aluminum on titanium nitride with 1 kV incident electron beam. Then I just tried to explain the reason between the difference in contrast in the center, and then you can see that the others rectangular region around it, and then the periphery region. So, you can see that a clear cut contrast difference between the outer region compared to inner region, and I said that the reason for becoming this particular rectangular region becoming dark is because of the contamination. So, if you expose this electron beam or a beam sensitive specimen like this for more time, then the built up of contamination is inevitable, and that is why it is very important that you do the recording very fast. So, you have to take that precaution, and then why this contamination is forming and the reason for the sample to be clean. That is something you have to be very clearly keep it in mind, and in order to do that, let me write some of the few important points. So, what I have written here is that if you look at the image what I have shown on the slide, we are talking about the contrast difference between the center region and the periphery region, and then we said that it is because of the buildup of contamination. And then, so the reason we need an uncontaminated clean specimen is very clear from this case study. There are three options commonly used to clean samples. The first one is a plasma etching before inserting the specimen in the SEM. The second option would be heating the specimen above 100 degrees centigrade to drive off absorbed gases and water. And the third one is swabbing the sample with a volatile organic solvent. It could be acetone, ethanol or methanol to remove the grease and oil. Of course, this option will only remove the soluble contamination. So, you need to follow any one of the previous two to remove the other contaminants. So, if you follow these things in the sample preparation, you can reduce the buildup of contamination rapidly, so before you grab the image. So, in spite of that, what you are seeing in the case study, even after the thermal etching is done, you see that the longer exposure of the electron beam on the specimen lead to contaminants buildup on the sample. So, now we will look at the cross section view of the same sample in the next study. So, what you are seeing on the screen is the secondary electron SEM micrograph of the thick aluminum film. Remember, one of the objectives of this case study was to look at the initial deposition of aluminum and its morphology. So, the earlier one what we have seen is a lower magnification, and then where you could see the grain boundaries and so on, and here you see that this is a higher magnification image, and then you see that a much more details are visible. You can see the porosity very nicely visible, and you have the very thick pores, and it is relatively a rough surface and some open voids like this. And the same specimen, a cross section view is shown in this second image, and again it is prepared by cleaving the silicon wafer together with aluminum, titanium nitride, titanium stack of films. The ductile aluminum shows a considerable plastic deformation compared with the brittle underlying layers, and a void is visible in the aluminum film. So, this is silicon oxide, and then you can see that the first layer, the contrast is not very bright here, but nevertheless you will be able to distinguish between these two. The first layer is where I have put the cursor, shows the titanium. The second layer is titanium nitride, and then you have the void formation here, and this is a ductile aluminum. You can see that it is a deformed layer of aluminum particle, aluminum coating I would say is sitting on this layers. So, you get a clear picture of these aluminum layers and on the coating, and the kind of defect it forms during the coating is also clearly analyzed during these kind of the SEM examination. So, that is another example where you can use this SEM more clearly. I will write some salient features of this. So, whatever we have seen on the slide on the coated aluminum, what we have seen is say the final thick aluminum film has got a different morphology, and SEM shows that open voids have formed during the deposition process. These voids are process defects which could affect the optical and other properties of this material. So, that is how one can interpret the secondary electron image in SEM in this case study. Similarly, we have just looked at the cross sectional view of this material, and where we looked at the thickness of titanium coating, titanium nitride coating, and then finally the aluminum coating. So, from this case study, and we have now clearly demonstrated how the SEM analysis is being used, and then the information is taken out for the appropriate interpretation and usefulness. So, I will now just move on to the other important use of this SEM in this case study called microanalysis. See, the microanalysis can be done in 2 or 3 methods depending upon the detection capability. See, one of the very common use of this microanalysis is done by energy dispersion spectroscopy or spectrometer, which is an attachment to an SEM or a TEM and so on. So, if you look at the slide, we have taken 2 examples in this case. The image what you are seeing is the same alumina, a secondary electron image, thermally etched alumina, and then EDS spectrum from the region is shown in A. Only aluminum and oxygen peaks are recorded together with the carbon due to the surface contamination. Please remember, when you do this microanalysis, you just compare the corresponding theoretical basis what I have given in the lectures in a theory class, where I have clearly shown the detection limit of EDAX, and that clearly shows that in order to obtain any useful information using EDS, you need to have that particular element to be present in the sample sufficiently. Beyond that threshold quantity, the EDS cannot detect. So, that is first and foremost important you have to realize before you go for this analysis, whether you have the elements sufficiently present in the sample. So, please refer those slides where I have given the detection limits for an EDAX, that is energy dispersive spectroscopic analysis, where I have given the different case studies as well. So, in this particular case, if you see that the spectrometers, the spectrum, the counts energy, number of counts versus energy spectrum shows only oxygen and aluminum along with the carbon, though the carbon is not intentionally added, it is coming from the surface contamination. And the other spectrum which is taken on the same sample shows a peak of oxygen, magnesium, aluminum and silicon. So, you should wonder why the difference between these two. So, let us read this caption first. EDS point spectrum recorded from a grain boundary in the alumina specimen. Aluminum and oxygen peaks are of course found, but also magnesium and silicon peaks, since these elements have collected at the grain boundary. In this particular case, calcium which was present in the specimen is either below the detection limit or absent from this specific grain boundary. So, the first and foremost important point to note here is the first spectrum is recorded on the grain, the second spectrum is recorded from the grain boundary. So, you can see that in grain boundary you are seeing additionally a magnesium silicon. So, there are two things you can infer from this result. That is, either the magnesium and silicon could be a segregation, but to make that conclusion you need to have a theoretical background about the solubility limits of this magnesium and silicon and aluminum. That is, once that is confirmed, then you can conclude this as segregation, otherwise you cannot conclude as a segregation. You can only say that magnesium and silicon present in the grain boundary maybe in the large quantities as compared to the inside the grain, where it may be there, magnesium and silicon may be there, but it may be beyond the detection capability of this EDS spectrum. That is how you have to interpret. But if you want to say that it is a segregation, then you need to have a solubility data and then say that it is segregation. That is another issue. So, similar point can be taken on the calcium observation, calcium peak observation. It could be same argument, it could be a segregation, or the quantity of calcium on the grain boundary may be higher than the inside the grain. So, that is another way of looking at this spectrum and how to interpret those. Remember, as I mentioned in the theory class, the detection capabilities of an energy dispersion spectrometer is inferior to the another similar technique called wavelength dispersive spectroscopy. So, where you can have much more resolution of this analysis. So, you can do the similar analysis if you have the attachment with an SEM. If you are interested in looking at higher resolution, EDS spectrum or microanalysis, it is always better to have a WDS rather than EDAX. But EDAX has got its own advantage, that means EDS spectroscopy has got much more advantage in the sense it is quite fast and you can quickly find out the result as compared to the WDS, which I have already shown in the theoretical analysis. So, if you look at the other case studies like this, what I have shown is a micrograph of a steel which shows a two-phase microstructure which is alpha iron and then Fe3C. So, this is in metallurgy, this is called this colony is called perlite, which consists of alpha iron and Fe3C. The black region is alpha iron, it is called ferrite. So, this spectrum, the first spectrum is recorded in alpha iron grain in a 1040 steel. This is a plain carbon steel with 0.4 weight percent of carbon. The carbon signal is far too high to correspond to the 0.4 weight percent in the steel, and certainly not to the residual carbon dissolved in the alpha iron. The signal is in fact due to surface contamination. So, you have to be very clear when you do an EDS analysis on a steel sample. As we are talking about this contamination, you get consistently this carbon peak in an EDS analysis. So, it does not mean that your sample has the carbon in solution or in higher quantity, and we also know that how the carbon is generated, cracking of this contaminants and becomes hydrocarbons and so on. So, in this particular case, the higher amount of carbon shown in the spectrum is not due to the carbon present in this steel itself. So, how to compare that? So, if you look at that other spectrum, the EDS spectrum taken from a perlite region in the microstructure as shown of the image, that means the first spectrum is taken from this region, second spectrum is taken from this region. You see that here also the carbon is there. So, this probably due to a carbon which is coming from this, because this contains an alternate layer of alpha iron and Fe3C. So, like that you can confirm this. See, the other example of this EDS analysis is shown here. This is an EDS line scan from a carbon signal and a secondary electron SEM micrograph of interface between perlite and alpha iron. So, you see that this is a scanned image taken from, this is the perlite colony what you are seeing here, and this is the ferrite grain, and you see that clear interface is shown here, and the analysis is done across this section is so called line scan. The corresponding count is shown here. You can make a 1:1 correlation between the region which is covered here to the counts which are shown here. So, you clearly see that as the lines, the scanning go through here. So, here you see that there is a peak, a carbon peak. Even the micrograph does not show the presence of the carbide here, but you see that a peak is there, and rest all you have a ferrite region, and finally it goes through another peak. It could be a carbide here, and then this is a ferrite. So, when you do this EDS analysis, you may find some of the chemical elements which may not be seen in a secondary electron image like this one. So, in order to confirm that, you need to do this analysis in 2-3 regions or as many regions as possible to confirm the presence of identifying the elements which is present here. So, what I want to conclude from this session of the tutorial is, first of all you have to choose what kind of a micro analysis you want to do, whether you want to find out the light elements or higher atomic number elements. Please understand, light elements will not be detected from this technique, and this technique can be used for higher atomic number elements, and then also the quantity or the concentration of each element to be analyzed should be present in the system in sufficient quantity, otherwise this technique will not capture those elements. And if you want a very find out the traces of the elements or the elements which are present in very small quantities, you need to adopt to another technique called WDS, or you have to go to a special techniques like TEM and then with attachment with electron energy loss spectroscopy and so on. So, probably those spectroscopy techniques I will discuss in another separate course, and where I am right now preparing those things. Then if you follow that, you can get to know how to handle those cases. So, I think with this I would like to conclude this case studies of SEM. So, I request you to go through these case studies, whether it is imaging or a microanalysis, along with the theory. Then I will just upload some assignments. You try to do that. The assignment could be, I will post some micrograph and I will ask you to interpret in terms of image contrast or in terms of microanalysis and so on. So, that will give you some confidence, and which again will help you in finally writing the end semester examination. Please remember, these case studies are taken from a standard textbook. I have given you a lot of references as well. You go through the same, and if you have a doubt, you can always write to me. I will just try to address those issues as much as possible. Thank you.